Oh, we did, thank you very much. It is just 10 to the 7th.
It'll be 39 million.
39 million?
Yeah. 953,300.
Oh, 39,953,000.
300.
Anyone else get the same thing?
I got
39, 88,
66 and
88, 66, and then 00? Okay, so a rounding difference somewhere. All right, we got 2 to get a third person?
I got the same thing she got.
Okay. So what you're saying is Caleb was just wrong. Okay. Caleb, what's up?
I don't know.
Alright.
Say calculate.
Alright, so I'm just gonna round that off to 40 million. 40 times 10 to the, 40 times 10 to the 6, or 4 times 10 to the 7. But that's not the speed. That's the speed squared. What is the speed itself?
$6,320.
6,320 units?
Meters per second.
All right. So we have the satellite cruising around at 6,320 meters per second. If that satellite went any slower, what would it do?
Would it be pulled into the?
Well, it is still being pulled in, but it's going so slowly that it would start to spiral in. And if it's going faster than that,
It would go out of the.
yeah, it would indeed go farther. And the gravitational force would weaken, and it would just spiral out and go hit another planet. All right, so we can figure out how fast it's going. How much time does it take to do that? Well, what's the formula for speed?
Distance over time.
All right. So that's equal to distance divided by time, and I'm trying to figure out that time. But the distance it's traveling, if it's traveling in a circle, what do we call that distance? The distance around the circle.
Circumference.
Yes. And you know the formula?
Pi times diameter.
Okay, that works. Or 2 pi r, depending on how you want to work it. All right, so it's pi times the diameter, or 2 pi times the radius. So this is going to be equal to 2 pi times the radius divided by, now I'm using a capital T here. The reason I don't use capital T for tension, I'm using a capital T to represent the period. For anything that has repetitive motion, capital T, the period, is how long it takes to do it once. So, give ourselves some room there. I'm trying to solve for time. I know my radius is 10 million, so I've got 6,320 is equal to 20 times 10 to the 6th times pi divided by my period. Set it up like cross multiplication. I multiplied the diagonal I know, divide by the remaining one. So 20 times 10 to the 6th times pi divided by 6,320. answer is?
31,232.
31232.
0.92532.
I'll just round that off to 3. Anyone else got the same thing?
And then would you divide that by like 60 and then another 60 to get like that?
Yeah, we'll get to that in a moment. You got something different?
I got 9,941.
9,941.
Mm-hmm.
Did you multiply by pi?
Yes.
Did you multiply by pi? Because 20 divided by 6 is roughly 3 and change. So I'm gonna figure that's roughly 3.
Oh, wait, never mind. I did it twice.
Okay.
Whoops.
It makes sense to be somewhere around 9,000 or 10,000.
I got the same thing.
Okay, so we're in agreement? All right, when we did this before, there were a couple people who did not get the same answer as everyone else when I had the mass of the sun there. Have you figured out what the problem was, or are you still having issues? Sorry to single you out, but Savannah, you had mentioned that you had gotten a different number.
Oh, when we fixed it, I got the same number, but
Okay,
it might have been that I did the parentheses wrong.
okay. Anybody having issues still with actually doing the calculation? All right, so we have 9,941. What are the units of this?
Seconds.
We're trying to find the period, so seconds. All right, let's figure out how many days that is. How many seconds in a day?
It's like 81,000, I think.
I call it 86,400, I think. But, all right, so let's first get it into minutes, and then we'll work from there. So I have 9,941 seconds, and I'm gonna multiply it times 1 minute over 60 seconds. And again, the math is legitimate as long as in essence, I'm multiplying by 1 because the numerator is equal to the denominator. Seconds would cancel out, and I'm left with minutes. So 9,941 divided by 60.
165.
155 minutes. All right, let's get into hours. So times 1 hour over 60 minutes. Minutes cancel out, so 155 divided by 60. Hours. So this thing's cruising around pretty darn quickly. So just a couple hours. So it circles the Earth a few times a day. Let's see how far away the moon is. Actually, let's figure out what the period of the moon is. If someone could look up the distance, Earth-Moon distance. There really should be a textbook in here at all times.
$238,900 miles.
Sorry, Earth, Moon. One more time.
238,900 miles.
238,000 miles.
Yeah, 900.
Let's get that into the cool units, metric.
384,400 kilometers.
384,000
400 kilometers.
kilometers, which is 384,400,000 meters. All right. We're going to go through the same process as we did before. We're talking about moon going around the Earth. What I did is, that was the calculations we did for some satellite, 10 million meters from the core of the Earth. This one, the moon is a satellite, it's circling the Earth. And so I have 6.67 times 10 to the negative 11 times mass of the Earth, 5.98 times 10 to the 24th, divided by R, 3.844 times 10 to the 8th. That'll give us the speed squared of the moon. Somewhere around 10,000.
Let's say 844.
844, yes. Levi, you look like you have it.
1.038 times 10 to the 22nd.
1.038 times 10 to the 23rd,
22nd.
22nd. That seems awfully high.
We're at 1,037,000.
1 million, so 1.037
7.
times 10 to the 6th.
Yeah.
Anyone else? You got this also? All right, so let's see, if we just ignored the number up front, so 10 to the 24th times 10 to the negative 11th is 10 to the 13th, divided by 10 to the 8th, which would be 10 to the 5th. And then I've got 40 divided by, okay, that makes some sense. All right, that's my speed squared, and so my speed
1,018.
1,018
0.64 meters per second.
All right. So it's traveling, because before we had it traveling 6,320. So the closer it gets to the Earth, the faster it's traveling. All right, so we now know the speed. We now need to figure out what is the time it takes to go around. So we're going to do the same thing we have over there. So my period is equal to the 2 times the radius, so 2 times 3.844 times 10 to the 8th times pi divided by 1,018.64. So that's distance divided by speed.
$754,731.
754,731.
731.
Anyone else get the same thing? Anyone get something different? Surely somebody else has done the calculation by now. Or is it complete faith in Caleb? Anyone? Your?
Is the number on the bottom 1018.64?
Yes.
I got 2,371,059.
59. Anybody get that? All right, we got one other person for that one.
I got 369,857.
Okay, so rounding difference. All right. I was thinking, my crude calculation in my head, I had it around 2 million. So this one seems more reasonable to me right now. Does anyone want to stand up and go, Caleb, how could you?
I'm throwing my calculator on, bro.
Okay.
It's gotta be,
Did you get to multiply by pi?
oh my.
That would do it. All right. Okay, so we have, what are the units here for this time?
Seconds.
Yeah. So we need to get it into how many days. So if we take, get rid of that. All right, so I have 2 million. Wow, much better. 2,370,000, we'll just round off, is seconds, times the number of seconds in a day, which is 86,400 seconds per day. That should be 24 times 60 times 60. So 6 times 4, yeah, I'm feeling good right now about that, until someone corrects me. And so we have how many days this takes.
27.44.
Which is about the right answer. It takes about a month for the moon to go around. That's the name month. And so roughly. All right. And so one of the reasons why the gravitational formula can be, it was actually adapted very quickly because there had been a whole lot of work done ahead of time, a whole lot of experimental data. Kepler came up with his rules and they could all be derived from this. So it was accepted rather quickly just because you could derive what was seen in nature. All right, questions to hear? Then let's do a more earthly pursuit. We talked earlier about if an object was traveling slower than the orbiting speed, that it would come spiraling into Earth. Likewise, if I took an object fast enough, so if I took my Earth here with a mountain and I shoot a cannonball off the mountain, well, it's going to fall. if I shoot it faster, it'll fall farther, faster, it'll go farther. There is a speed at which it will go all the way around, and that's what we call a satellite. But what I'm interested in right now is the falling bit. I know that if it's shot fast enough, I have to take the curvature of the Earth into account. My orbiting speed is going to happen when the curve of the fall matches the curve of the Earth. I think it was either Phantom Toll Booth or Wrinkle in Time. I think it was the Phantom Toll Booth, where one of the characters would fly by throwing themselves at the ground and missing. That, in essence, is what a satellite is. It's falling towards the ground but constantly misses. But let's turn to falls to the ground and hits it. And let's go with a short enough scale so that we can assume the Earth is flat.